Jin. Shudong came to Case in 2004 after finishing his PhD at Boston University. While there, he was a recipient of a prestigious IBM PhD research fellowship, and since then he's been very successful in the area of the general area of networking. He's published on 30 papers in prestigious venues. He's served on a number of program committees, including prestigious conferences such as ICMP. His, as I mentioned, major interests are in the general networking area, in the multimedia streaming protocols, and so forth. And it's a pleasure to have him as speaker today.
Okay, great. Thank you for the introduction. Today I want to talk about some relatively new topic, the so-called network coding technique. And then I will also talk a little about some ongoing project I'm working on. And because this is a relatively new topic, so I think in order to explain this better, I think it's good for me, better for me to start with some background on the current modern computer network design. So the first background is the end-to-end design principle. For more than 30 years, this end-to-end design principle has been applied to especially this internet system, and because of this design principle, the modern computer network architecture has this so-called the property called dumb networks smart terminal architecture. So it means the network core is really simple. So in the middle of the network, the routers, the elements like routers, will do very simple work. But the end host will be very smart. They will do more work. For example, user interface, enforcing some reliability. Okay. And this principle also says that the function and capability implemented in the core, network core, may be redundant. And if we implement all those function and capability in the middle of the network, they may not be used for some particular, for many applications. So in that case, certainly we do not have to implement that function or capability in the middle. Okay, so that's the basic design principle. And related to these, so we have this so-called Internet Protocol Stack. Okay, so if you took a computer network course before, then you probably know the Internet Protocol Stack. We start with, on the top, we have the applications, and the applications will communicate with each other by using some transport layer protocols, and TCP, UDP, right? And for example, you use a web browser, it will use TCP to transfer some files from the web server, okay? And then below that, we have the network layer in the Internet Protocol Stack. So this dominant, the most important protocol is the IP, v4, v6. And then below that, we have more link layer protocols, including the MAC layer protocol and some physical layer protocols. Those are very related to these hardware systems. Okay, so you can see from this picture that everything above this network layer, so it means applications, transport layer, they are implemented in the end hosts. So the upper layers are in the end hosts only, okay? And the network core will implement IP, the network layer, and everything below. Okay, so that's the protocol layering. And of course, this protocol layering has some other considerations. For example, it's easy for us to implement a system if we have many layers. It's good to have software modularity, and also we need to consider hardware heterogeneity when we consider different low layer protocols. Okay, now let's go to the topic. So because of those design principles and protocol layering, so we have these so-called modern network computer networks are packet switching or packet switched networks. Okay, so what is packet switching? So it means when we send a file, we will divide a file into many small packets, small units called packets. Then the packets will be sent to the destination, and the modern computer network, especially the internet, will simply forward those packets towards the destination. And those packets may go through many hops in the middle of the network. Okay? So the core of the network will perform two main functions. The first one is routing. Okay? So routing means we need to decide the path from the source to the destination. What is the optimal path? Or sometimes it's not easy for us to find the optimal path. Maybe we can find an efficient path. Okay? And those are routing algorithms. And then we need to design some protocols. Some protocols will implement those algorithms. Okay? So that's the routing part. I'm not talking about routing today. Network coding is mostly related to this forwarding. Okay? So what is the forwarding? So forwarding, in the forwarding architecture, so the computer network simply do the simple store and forward function. Okay? So what does that mean? So if we have this computer network with some routers in the middle, so this router will receive some packets from some incoming links, right? So those packets will go to this router, and possibly if this router cannot forward those packets as fast as the incoming rate, then it will keep them in the buffer. So that's called queuing. Okay, put them in this queue. And when the link is it is idle, so then we can send the packets to the next stop. Okay, so we will have a sequence of packets, outgoing packets. And with this simple store and forwarding architecture, the most important feature is that we have minimal modification to the packets. Means the minimal modification to the packet header. So sometimes we need to modify, add some header information, or maybe modify some bits in the head. But we will never modify the actual content within the packet. Okay, so the network itself is really dumb. Just do forward the data without modifying it. Okay. Now, what is network coding? So network coding is different. Is unique is that it breaks this store and forward assumption. Okay, and network code will let the network core perform coding decoding. We know some coding decoding techniques, right? For example, we can have some forward error correction technique adopted by used by some end hosts, but that is done by the end hosts only. The network itself will just faithfully forward the packet as it is, right? Okay, now with network coding here, an outgoing packet can be a coded one. So just look at this example. So this is a router, receive A, receive B. Okay, so normally we should forward A and then B, or maybe first A, B, and then B, then A, right? So now with network coding, we can actually do, this. I call this mixer. Can mix these packets together and send out a single packet. I use this very simple function, this exclusive OR operation. So basically, packet A exclusive OR packet B. So we generate another binary bit sequence. Okay, so you may have some questions here, right? So because we want the objective is we need to forward A and B towards the destination. But this one is useless, right? to the destinations. But if we look at a bigger picture, can be useful. So let's look at this example. So in this example, we have two senders, S1 and S2. We have two receivers, T1 and T2. Okay, so both T1 and T2 would like to receive data A from S1 and data B from S2. So it's a group communication scenario. Okay. Now, without using coding, you notice that A can be forwarded along this path, B can be forwarded on this path, right? Now, this node can receive both A and B, and it can forward A or B, right? But not A and B at the same time. So basically, this link will be time shared, between two flows, time shared by the two receivers. Okay, we can first send A, then send B off, then first send B, then send A. So it takes 2 units of time to send 2 packets. But if we do send A XOR B together in a single packet, now this one has A XOR B. So now this one can send A XOR B and A XOR B to both receivers. And now for T1, for example, it has A XOR B, it can find B, right? Do some calculation. Basically B will be the the result of XOR of A and A XOR B. Okay, so you notice that with this network coding, we can have actually improved receiving rate for both receivers, right? Okay, now let's go to, this is an example in a wide network. Now let's talk about wireless network and why I want why wireless network network coding is especially attractive. Okay, and there are various wireless networks. For example, mobile ad hoc network, MANET. We can have mesh networks. We can have even some sensor networks. They can potentially use network coding too. Okay, and all those networks have broadcast capability. A single broadcast can be heard by many receivers within the range, right? Okay. But if that's possible, then it is actually a waste of resources if we do not utilize this capability. Okay. So if some node receive that packet, it's not for itself. So this packet will be simply discarded. But if we keep it for some, maybe it can be useful. And network coding can be used to explore that benefit. And the benefit of coding in wireless network can be especially attractive because of the limitations of those wireless networks. Those wireless networks, for example, mesh networks, can have low capacity. We hope to improve the capacity of this mesh network. For mobile ad hoc network, maybe they have very high loss rates. So we want to improve the reliability by using coding. Okay, so maybe for sensor networks, so sensors have very low energy supply. So we want to try to utilize the resources, the broadcast capability, to save some transmission. Okay, so I think there are broad applications in wireless networks. Okay, now let's look at wireless network and see the first example showing why broadcast can be useful, together with coding. Okay, so let's look at this example. We have two end hosts, this one and that one. Okay, and they want to exchange some data. So basically, we will have two sequences of packets. A sequence of packets A will go from this sender to that sender. And a sequence of packet B will go from that sender to this sender. Well, they go through the, they will go through the reverse path. Okay, assume they will on the reverse path, and they will go through some central node. I call it a mixer. Okay, and you notice that the mixer, normally if we do not have network coding, then the mixer, any node actually, needs to forward 2 packets, right? But if we have network coding, this mixer receives both A and B. And it knows this one has A, this one has B. So why does it need to, broadcast both A and B, twice? Why not just broadcast A XOR B just once? So how much saving here? 50%. Transmission has been saved, right? Okay, so that's the benefit. Okay, now let's look at probably a similar but probably a more interesting scenario. Okay, so in this picture we have actually very similar to the previous example, except that we can have overhearing. Overhearing means a node can hear some transmission for some other receivers, not for itself. Okay, so now S1 in this picture, in this example, S1 wants to send packet A to T1, and S2 wants to send packet B to T2. Okay, and in the middle of this network, we have this mixer. Okay, so where an intermediate node here who wants to receive B can overhear a broadcast by this node. This is the packet A, right? So it can get a copy of this A to its buffer and keep it. And this node can also overhear the transmission of a packet B here and keep a copy of this B in its buffer. Okay? Now, this mixer, if it can know that both of them has a copy of the packets, then it needs only to broadcast A XOR B.
How can it know?
Well, there's of course a implementation details. They can exchange some messages.
Also, is there? Oh, I see. There is no probabilistic reasoning here.
Right.
By exchange.
Can guess it, right? So this node will know the network topology in this neighborhood, and know that this one can overhear, and this one can overhear. Okay. Okay. Well, the effect actually is the same as the previous example, right? Okay, now, in the previous examples, I show that network coding can be used to improve the capacity of the network by reducing the number of transmissions. Okay, but do we have some other benefits of using network coding? So let's look at other than increased capacity. Well, there are lots of research on showing what is the potential benefits of network coding in improving network capacity, and people find usually some theoretical study find the bound on that, like they can improve can be some percentage, not like how many times 10 times. It never happen. It will never happen. So the improve power is more like 10%, 20%, or even lower. Okay. But we can. So this one can be very limited, especially if the network is under provision. It's over provision. Okay. So But we can explore network coding for other benefits. And reliability is an example. So think about this. If we save the 10% capacity, if we just invest this 10% saving back to the market, maybe we can result in a 10 times reduction in wireless link loss rate. So add more redundancy. Probably it's a good trade, right? So let's look at more examples. So in this example, we have 3 flows. They form a triangle. So we have 3 receivers, A, B, and C. Actually, each of them is also a sender. So A send packet A to B. B send packet B to C. C send packet C to A. So it's a triangle. Okay. Without network coding, this central node needs to do broadcast 3 times for 3 packets. Okay. Now with network coding, you can notice that this mixer is only to broadcast A XOR C and A XOR B, only 2, right? And this one, this node A, receiver A, wants to get C, so it can actually, because it has A, so it can recover C by receiving this. And node B can recover A because it has B already. Okay, and the node C can recover C, where it has C already. It needs B. But if it will receive both packets, we can XOR 3 packets together, and we get C. Okay. So that's the case with the simple coding scheme. So basically, we broadcast 2 packets. Okay, so we save some, like maybe, what is the percentage? 1/3 of the transmission at this central node. Okay, so a sizable reduction. Okay, but can we use this scheme to improve reliability of those wireless communication? So think about this scenario. How about we let this mixer, this central node, broadcast all 3 packets. Now we still broadcast 3 packets. Instead of the original packets, we broadcast 3 coded packets. Do you think we can benefit from that? If anyone is lost, you lost 1, you can still recover. You lost 2, well, you still can.
Oh, you still can?
It's still possible you can recover 1. Okay, so let's look at this picture. So assume we have a uniform. We can do some calculation. Okay, so assume a uniform and independent loss rate P of the 3 outgoing links from this central node. Okay, so we have loss rate P here, and P here. Okay, and this redundant coding scheme will increase the probability of recovering the needed packet at every receiver. Okay, so just to look at a single node, node A can decode C. Node A wants to get C, packet C. Okay, node A can decode C if it receive A XOR C, because it has already it has A, right? Or both A XOR B and B XOR C. Okay, if it has this one, it can just recover C by XOR A and this one. If it does not receive this one, instead it receives these 2, it can still XOR 3 packets and get the needed packet. Okay, so the probability, we can do some simple calculation based on the independent assumption. Then the probability can be calculated in this way, and I ignore the details. So the result will be like this. Okay, so that's the probability that it can recover the packet. So the loss rate. What is the loss rate? The loss rate was p, right? And what is the loss rate now? It's 2 times p squared minus some, even less significant one. Okay, so do some simple calculation using some values. So p, if 20%, it will be reduced to 7%. If it's 1%, 10%, it will be 2%. Okay, so it's 5%, half percent, 5%, then it will be 0.5%. Okay, 10 times improvement, right? Or 10 times reduction in the loss rate. Okay, so that's probably a more attractive scheme by using network coding. Okay, but I want to say that nothing is free, right? There's no free meal. So the problem, well, the first important problem is that we need to think about how we can actually implement such functionality in this system. Okay, so we know that this is the internet process stack. Where do we implement this coding scheme? So this coding scheme will involve actually maybe several layers, right? So the packet will be, we will do overhearing at the MAC layer, MAC sublayer. We will do the link layer. We need to manage the, modify the routing or forwarding architecture. Okay, so basically it will change the link layer, including the MAC layer, and this network layer. Okay, so if we implement some function in this architecture, where do we place it? There's no answer to this, no solution to this problem. But I do think that it should be somewhere between this network layer and this link layer. Okay. Well, there are some other problems too. For example, how do we know there is a coding opportunity? Right, in the previous examples, we know that we assume that the mixer, the central node, knows everything in the neighborhood. But how can it know? Okay, and in order to know that, we need to know the network topology at the time, right? Especially if it's a mobile ad hoc network, the network topology can evolve over time. So how do we know at a certain point of time we can still have that coding opportunity? And also, we need to know the traffic patterns. How do we know the packets can be, the pattern can be explored and use network coding to reduce transmission. Okay, so it's not easy actually. There are many details, and we did some experiments. So this is just a very simple experiment. We implemented network coding, try to implement this coding scheme for a simple scenario. We use a popular network simulation software called NS2 simulator. Maybe some of you know this software. And in this implementation, we assume the receivers will overhear our broadcast packets. So we need to modify the MAC layer and the link layer modulars, okay, in the NS2, and they will be able to monitor the packets that have been received and then recover the needed packets. Okay, and then the router or the mixer in the middle will try to buffer the packets for potential coding opportunity. So it's basically some opportunistic scheme. So put some packets in the buffer, wait for some time period, see if more packets will come. If yes, we just mix them using XOR and send out using broadcast. If not, we'll wait for a certain time of period. Okay. Okay. And then we did some experiments to see what is the benefit of this coding. Okay, so some configuration, we use wireless network, we use 10 megabps broadcast channels, and assume in this example, we assume there's no link loss. Okay, but we do have congestion losses. Eventually, the rate should be limited. And we run very long simulation. We use TCP, you simulate TCP flows, and then we compare throughput with network coding and without network coding. See how much we can save from these in this scenario. Okay, so what do you expect? Do you think that we can, because of this coding scheme, we can broadcast 2 packets instead of 3? Do you think that throughput can be increased by 30%? No, that's probably some theoretical result, right? In implementation, never happened. So how much do you expect?
What?
10%, or 0%, or well, actually very disappointing for some reason. Okay, so without network coding, we have 3 flows. They have each of them gets half megabps. Well, with network coding, something went wrong. The throughput actually is reduced. Okay, so actually there's a 18% reduction in the throughput, in average throughput. So what happened? Well, it's all about the added delay. Because we need to have coding, we need to let some packet wait, right? And that waiting time is actually fatal to the TCP flows. Okay, so we buffer the packets. Then the upper layer protocol, we use TCP. Just want to mention again, we use TCP. Okay, so TCP will react to this added delay in its unique ways. So do you know now? Yes, some of you know TCP, right? And the design of TCP. Right? Because packets are buffered, the round trip time of each packet is increased. And perhaps this round trip time also become very variable, right? Highly variable. Can be, some packets will be delayed for a longer period of time. But if there's a coding opportunity, the packet will immediately go out. Okay, so the variation can also be very high. And the TCP sender will estimate the round trip time and set some timer accordingly, right? And that timer is important. When timer expires for a packet before the acknowledgement for that packet returns. So TCP will assume that it cannot indefinitely wait. So it will assume the packet is lost in the network. Okay? So if a packet is lost, what does TCP do? Do retransmission, right? Before that, but need to reduce the rate to be more conservative.
Are you saying you observed that?
Well, yes, I can see that. Okay.
Were the buffers limited at the was the question over?
The buffer size, what do you mean?
At the nodes where the buffer size is limited or unlimited?
Oh, the buffer size, currently we do not limit the buffer size. That's the problem. Okay, so yeah, actually you asked a good question.
It might not be a problem because if you store, unneeded
Yes, we can set
packets
some
in the-
threshold there, like limit the waiting time for some certain period of time, right?
But then for new packets, you could drop them because your packet is your buffer is full of unneeded packets.
Oh, you mean the buffer size? Buffer
Right.
size is almost unlimited here, so it doesn't matter because as long as we have a few packets, we can do coding. So the buffer size doesn't matter at all actually.
So what is the problem that you were referring to?
The problem.
No, in response.
He was talking about how long does it. I thought he was asking, you know,
Right,
how
so
long
that's not
does
a
it.
problem, but you said that there's the problem with the buffer, but what is the problem?
Oh, the problem is that we need to decide how long that we let a packet wait
I see.
until it will give up.
I see.
Okay, we cannot let it you know, wait there for any arbitrarily long time. Okay, so because of this, the timer expires for a packet, and it happens more often to the case without network coding. Okay, because of this reason, the rate will be sending rate of the receiver will be decreased. Okay, so as a result, the overall throughput actually decreases instead of, you know, we have increase. Because of this, we have, you know, probably, you know, frequent timeout, and then the rate will be very low, and we do retransmission, and if we have a lot of retransmission, basically consume resources, the wireless channel, right? Okay, so overall performance actually decreases. So of course we need to find some solution to this problem, right? So one solution might be, you know, we want to limit the delay we can allow a packet to have in the router. Okay, so if after some certain small delay, if we cannot utilize this coding opportunity, then we just give up and send out the original packet. So that's a potential improvement. But certainly, you know, because of those details, we will not be able to, you know, expect a 30% increase in throughput. Okay. Okay. Now let's look at one more example. See, this coding has other problems. Okay. But even if we can implement efficient network coding scheme, and we can fully, you know, exploit the benefit of improved capacity, we still need to care for its impact on the other layer, especially the upper layer, where the previous example actually already show this point, right? Demonstrate this point. Okay, so the layers are not independent, and network coding capability basically can change the underlying, you know, demographics of the traffic. Because the coding, we can change, for example, the loss rate of the flows at the link layer, right? So because of this reason, the input to the upper layer is already different. Okay, because of those added low layer capability of function, the input to the upper layer will be different. Okay. And let's look at an example. In this example application run, we still use this triangle of 3 flows, and assume we use TCP for file transfer. And here, of course, the goal is to maximize the throughput. And network coding may improve the aggregate throughput if we can, you know, have a good design. Okay, not like the one example I used before. Okay, so assume we can do that, but is that enough? We can improve the aggregate throughput, but doesn't mean that everyone will get it, right? Maybe some of them will lose actually. Okay, let's think about this example with a simple, non-redundant coding scheme. And 3 receivers will be able to assume we have the same loss rate for those outgoing links. And the 3 receivers actually will experience different probability of recovering the packets. Okay, so A needs to recover C. So it has A, so it needs only A XOR C, right? And B needs only A XOR B in order to recover A. And C needs both. So if there's a loss rate P on the outgoing link, so C will have experience almost twice the loss rate. Okay, does it affect the application performance? Actually, it will. Why? Well, TCP flow throughput is inversely proportional to the square root of the loss rate. If one flow experiences much higher loss rate, it will likely get a much lower throughput. Okay, so when they compete against each other for the bottleneck here, so the third flow will get much lower bandwidth. Okay, so here you can see actually network coding, although can improve the aggregate throughput capacity, it actually introduced some artificial fairness.
You just need to sort of alternate which
Yeah, actually, that's a good. Actually, I want to talk about that in the next slide. Well, now this one. So, the redundant coding case. The previous one is the simple coding without redundant packets. Okay. Now, if we add redundancy here, we want to improve the reliability. Okay. But we consider this scenario. So the loss rate of those outgoing links can be different. For example, this one P, this is twice P, and this is 3 times P. Okay. Now, every receiver needs to receive one packet, or maybe the other, or the other 2 packets in order to recover the wanted packet, right? Needed packet. So then we can calculate the loss probability. And I just ignore those details. And actually, we will notice that the loss rate for these 3 flows will be about this. The first flow, twice P squared. The second flow, 8 times P squared. The third flow, 18 times P squared. Okay, means actually, initially the loss rate is not, they are actually close to each other. Now, the loss rate has been reduced, but the difference, the relative difference actually is bigger actually, right? So potentially, but I'm not very sure because there are some other reasons to affect TCP throughput. But potentially, this more skilled loss rate can result in even more skilled throughput among those application flows. Okay. Okay, now let's look at some possible solutions for the simple coding scenario. Okay, so in that scenario, we can just need to schedule the network coding delivery to achieve both efficiency and fairness. In order to achieve fairness, actually, we can use some round-robin scheme. It's a very simple idea, right? So first time in the first round, we broadcast the A XOR B and the A XOR C. And in the next round, we will just switch, go to A XOR C and B XOR C. And then broadcast the third combination. Okay, so we have 3 packets. We can broadcast any 2 of them with some take turns, and that's okay, right? So this one will work in this case for this scenario. Okay, of course, where the loss rate can be different. If the loss rate can be different, and we want to improve the fairness among the flows, we can maybe slightly modify it.
Why is fairness a criteria for you?
Well, of course, we do not want to have some flows whose throughput is very low.
Why? So long as you have a minimal guarantee, why is fairness an issue?
But the minimal is not guaranteed, right?
You have to have a worst case guarantee. Other than that, I don't think fairness is an issue.
Do you think it's okay that some flows will have very low throughput?
So So long as you have a guarantee of the worst case.
Well, no, there's no guarantee of the worst case.
No.
Right.
The worst case I thought would still go back to your probability P loss rate, which is still acceptable, right? In other words, you are doing opportunistic improvements.
Okay, the problem is that because the loss rate is become more secure, so these flows will compete against each other. If someone else gets more, then means you will get lower.
And still you will not have a worst case guarantee.
No, actually can be worse for the unfortunate one.
I see.
Yeah, but we want to guarantee that it will not get worse.
No,
It
but
will
my
be
question
even more
was,
fair.
My question was, are there more sophisticated algorithms to even rearrange the buffer so that can you afford the time so that you provide worst case guarantees? With that, you don't deal with the additional complexity of guaranteeing fairness. So that you don't have to move into these schedules such as you have to do round robin schedules.
Yeah, I think in order to guarantee the throughput or some other performance aspect, we can have some like a quality of service schemes to do like scheduling of the packets in a smarter way, but those schemes also have some added complexity or they require a lot of implementation efforts.
I have a riff on that, which is, I wonder if you can comment on, so GCP is not fair.
GCP is not fair, right?
It is not fair. Arguably, that was never its goal. So I wonder if you can comment on sort of whether this is in the sort of general realm of unfairness we already have for TCP, or is this making it, very, very egregiously unfair?
I think I agree, TCP is unfair to the flows. But that should not be a reason that we can use network coding, by make it even less fair.
Yeah, I'm trying to understand what network coding does to the fairness. Does it change it a lot? Does it change it a little?
I don't know. So this one, we haven't done any simulation of this, this scenario. But in the previous example, I see, we have the third flow has twice the loss rate. Then I would expect maybe the loss in the throughput of that flow will be maybe 40% lower than the other flows.
Yeah, but simulation will give you expected behavior, will give you clues on expected behavior.
Right.
What I was saying was minimal cost modifications to your algorithms to provide worst case guarantees and then ignore the fairness issue, just deal with efficiency. It's a more philosophical.
I agree, but how do we don't know what is the the minimal guarantee for TCP especially. There's no guarantee at all.
Let me rephrase. Minimal improvements or changes to your algorithms, minimal cost changes to your algorithms, so that you are the expert. I'm just giving you my opinion, so that you will not deal with the extra cost of guaranteeing fairness. You will not move into these scheduling algorithms. You will only deal with the issue of efficiency, together with the improved loss rate performance.
Yes, I think it's possible for us to to theoretically study the worst case performance fairness problem, right?
No,
maybe
what Tikin is saying is that since you already in general, IP networks, it's difficult to maintain any kind of per flow guarantees because routers don't maintain any per flow state. In your case, you are buffering some information about flows already, and so perhaps this information could be utilized for to enforce some more fairness. Because you're maintaining a little bit more information than normal routers do. So
then I agree. I think maybe in combination, we can combine this network coding scheme with some quality of service scheme.
It's
to
because you have
yes.
some buffers already.
Yes, I think that's a good point to have some
How-
quality of
how-
service guarantee plus performance improvement.
How would any other scheme would be simpler than just this simple round robin thing?
I don't know.
Yeah, I mean, there is an overhead even with implementing round robin, right? There is.
Right.
So I'm assuming that you are tightly controlled with your overhead with these algorithms. So my question was, can you do better than?
Okay, so continue, and actually I'm concluding my presentation. So this is an ongoing project. I'm still working on it with some students, and so we are making progress on that. So, but we certainly can summarize some, some points here. So first, the potential of network coding. So it's a new networking paradigm, and it can be useful in many scenarios. And it has limitations too, especially we have some pitfalls, be careful, especially on protocol design, and especially the interaction between different layers of the protocols. And there are also details on how actually we can implement this capability in real systems. And of course, there's some more bigger picture problem, like how we can integrate these functions into the existing network architecture. And we may even ask, does it follow the fundamental end-to-end design principle, or does this performance benefit really justify the inclusion of this new function? Okay, so I think there are many open research problems in this field. Okay, so a couple of references, mostly some tutorial references. There are lots of papers on this topic. I cannot include them, like maybe 100 papers already in this area. But it's a relatively new research topic. Okay, I will take more questions.
So,
So this is a question, probably network coding makes my head hurt, but so this is kind of a background question, I think. But what I don't understand is this all looks great when you have A, B, and C. But what I don't understand is when you take two packets, especially at the MAC layer, and you mash them together, and then I get that resulting packet. It's just a bucket of bits, right? I mean, how do I know how do you do naming? Because naming doesn't have to way up here, right?
We can still have the original header. We can add maybe a few, we can do like a tunneling thing, or we can add some new header to that one if we have a sublayer. Okay.
Which
so
header do you put on?
we can have this mark layer.
Yeah, but you're mashing multiple packets together.
Yes, then we can have the content will be mixed.
So you're gonna put two.
But the header probably will not be mixed. The MAC header will not be mixed.
You're gonna put two MAC headers on. Is that what you're telling me?
Well, we can.
But I still don't understand because the MAC header doesn't name the data.
We can have for example, another header, just inside the MAC header. You think possible? Like
Well,
inside
that's
the
what
MAC
I'm
header.
asking. I mean, you implemented this in
Yes,
some fashion.
I didn't implement these, these actual package design, header design, for in this simple scenario, but I do think that's the way to do that.
another question. So with the packet losses, the TCP steps back and then underutilizes the capacity. When you reduce the network, when you reduce the loss rate for everybody, and then you're saying, okay, so you reduce the loss rate for this guy more than for that guy, and therefore you increase the unfairness. It's kind of like, if I paraphrase, our politicians, I gave like a huge tax cut to this guy and a small tax cut to this guy, but both of them get tax cut, and so no one should object. So to me, if you improve the throughput of all three flows,
Okay, actually, in my example with like in some examples, it's possible that two flows will gain, and the third flow will actually lose some.
okay, that was what I was
Yeah.
wondering.
So we want to avoid, certainly want to
That
avoid that.
definitely want to avoid, yes.
Is the idea that every packet would be coded at a particular router, or the router would decide which one?
No, the router will decide it's opportunistic means if we find that there's an opportunity, it will code the packet. If not, send out the original packet. Anyway.